Matt, on to you.
Awesome. What I'd like to talk about today is thinking about human machine learning systems. So you could think of human AI in general or human and ML. So if we think about maybe many of us, when we think about what the future is going to look like, we think about Rosie the robot. So she goes around and cleans and talks with us and does all this stuff for us, and we are still not there in the 2020s. One thing we can do now quite successfully is what are called centaur systems. So you may remember from Greek mythology, centaur is half human, half horse. And modern centaurs in general are part human, part AI. And what I'd like to argue today is that in some cases, we do want complete autonomy. But even if the eventual goal is complete autonomy, we might be better off starting with an agent or a ML system that's working with a human. So, where do we really want autonomy? One of the places are when things are dirty, dangerous, or dull. So here's a picture of a miner from 1908, 11 years old. Probably not the best job for a person, certainly not the best job for a child. This is exactly the kind of thing we would want to automate and let some kind of autonomous system just do the thing. Another time autonomy could be useful is to let us enable completely new things. So autonomous robots completely change the assembly line. Now remember, most of these assembly robots are quite dumb. They're just going to do the same action over and over and over. And if a human gets in the way, sorry, human, tough luck to you. But now these robots are becoming more not only autonomous, but also more aware of their environment. And autonomous systems lets us do things like have new modes of delivery, where if we've got a bunch of drones flying around, you're not going to have one person or three people monitoring each drone individually. These drones have to be autonomous. When we think about autonomy and AI, there's really two kinds of motivations. One is that, well, if you're going to use autonomy, it's going to help you do things. But there's also if you're not using autonomy, your competitors might be, so you could be left behind. So this has gotten a lot of companies, a lot of people thinking about how can I automate things, and that often turns into thinking about how can I replace people with machines, and that's often not the right way to think about it. I would argue a better way of thinking about it is how can I get people to do things they're better at while the machine does the boring stuff? Or how can I get the machine and person to work together to produce something better than if just the person was doing this thing? So some places where you would not want autonomy, one of the places is in life or death situations. It can be very hard to trust a robot. And you may not, if you have the choice between a doctor who's a person and a doctor who's a robot, many people will feel more comfortable with the human doctor, even if they happen to have the same skills. So it can be really hard for a person to trust an autonomous system. Now, another case where this comes up is thinking about ethics or making ethical decisions. So in this case, you've probably seen this before. This is the trolley problem, where there is a trolley going down a track, and the person could either pull the switch and the trolley will divert and kill one person, or not pull the switch and the trolley will go and kill 5 people. So many people would argue, oh, well, you should pull the switch because it's the greater good. Some people will argue, well, you shouldn't do anything because neither choice is good. And by you taking an action, you're endorsing something. So there's this cool experiment called the moral machine. And that was at MIT. And they did a modern version of this with an autonomous car and said the autonomous car is either going to hit 2 adults or a child. or it's either going to hit 3 dogs or a pregnant woman. And they had all of these different decisions. And the big thing they found is that, not surprisingly, different people made different choices, but also those choices were regional, that different people around the world would have different biases. So not only are machines ill-equipped to make these kinds of ethical or moral judgments, what is actually ethical could be very dependent on who's involved. So that's probably not something you're ever going to be able to automate, at least not in the near future. So instead of thinking about how could our autonomous cars automatically solve the trolley problem, wouldn't it be better if there are ways that we could come up with human AI systems? So the way I kind of pitch this is you could think of that it's really a range. So you could have just the human or just the robot. And then in many cases, you can have some kind of combination. So let's say we still want it to be really human focused. Well, we could have an agent providing some advice or providing some extra information to help you make a choice when it thinks it's relevant. Or maybe the system could help make recommendations. Or on the other end, you could say, well, the robot's going to make the choice, but the human will just confirm it. Or the robot's going to act, but then the human can always hit the emergency stop. Or the robot's going to act, and then a human will review those actions after the fact. So there's an entire range of how much autonomy the system has versus how much autonomy the human has. And one of the things I'd like to try to argue in this talk is actually at this intersection where the human and the AI are interacting, you can actually come up with a lot of good solutions that are better than you would get with only AI or only with humans. So I'm going to try to argue that this is an important thing to know about. I'm going to give a few examples of this kind of thing, and then I'm hoping we can have a bit of time to do some brainstorming about where taking an automated solution and putting a human in the loop could help, or taking a human and adding some automation or adding some AI to that could help. Right. So autonomy is awesome. If you can have robots do everything for you, if you can have agents solve all your problems, good on you. Some cases you don't want that. In other cases, you may not just be able to do it at all. So the first example is the Mechanical Turk. So hopefully you've seen this before. So this was 1770. This guy wanted to impress the Empress of Austria, so he made a robot that could play chess. And it was not a robot that could play chess. This was 1770. Instead, he had a very small person underneath who was very good at chess. And the small person was able to move the levers around, so it looked like the Mechanical Turk was beating all of these chess people. So, okay, that's kind of a gimmick. That's kind of cool. Go from the Mechanical Turk to Amazon Mechanical Turk. So hopefully you've also heard about this. The patent for this was filed in 2001, about 20 years ago. It became public in 2005. So it's been around for a while. And one of the big things Turk accomplished was getting a lot of people to answer a lot of simple questions. So for instance, is this a cat? And yes, no, or maybe. And by doing this, they could get hundreds of thousands of people to give them data, and that fed in to early deep learning algorithms for vision and let them find all the cats in a picture, for instance. Because with supervised learning, you'll need lots and lots of data, and it can be really hard to get that if you don't have a human. So in Mechanical Turk, you have hits, human intelligent tasks, and those go to Turkers who solve the hit, and then that gives you data. Now, there are some open questions about this, things like, is it reasonable to ask someone to do something really boring and pay them less than minimum wage? Well, you probably argue that's not all that ethical. Well, but what if they're not in Canada? What if there's someone with a minimum wage is much lower? So, okay, you can make some arguments there. But you could also, one of the big problems is some of these people are going to go and try to make some money. And if they're trying to make money, they may be trying to get through these as quickly as possible. Rather than giving you really high quality data, they're just trying to do their thing very fast and go to the next screen and get paid their 25 cents. So one of the things you have to do is worry about, how can I make sure that these Turkers are giving me good data? And if the data isn't good, then how do I make sure, even if I do have to pay them and waste some money, how can I make sure to at least exclude that data from my data set? So that's Mechanical Turk. That's a simple way of getting human level intelligence. I shouldn't say simple. That is one way of getting human level intelligence into your program or your code base. So one example that I really like of Mechanical Turk is from Walter Lasecki, and he's at the University of Michigan. And his scribe system was saying, I want real-time captioning. And right now, the systems for captioning really aren't good enough. Instead, I want to have humans help me do this. Well, it's going to be impractical to pay 100 people to be on call 24 hours a day. So instead, he's got this idea, Legion, where when you're going to need to do something, when you're going to need to do some transcription, you get a bunch of people to sign up. All right. So try to get them and say, okay, I'd like you to be available, within the next 15 minutes. Then as speech comes in, then what they do is they take these different snippets of speech and focus different Turkers on different parts of the sentences. So first on the part of the sentence someone else is handling, they go fast, and then on your part of the sentence, they slow down and then speed up again. And there's going to be some overlap. So what they're able to do is give the Turkers extra time to type out their part of the sentence, and then they can look at overlaps and make sure they agree, merge them together. And then even after merging, you could also have somebody else that's just looking and saying, is this okay? Because typing, for people who aren't expert typists, it's quite hard to type at the speed someone's talking. But if you can read at the speed someone's talking. So if you're able to just read and make sure there are no bad errors. So that's, some people are doing the typing and some people are doing corrections. And then you get near real-time captioning for speech. So this is an example of something where there is no current good solution for captioning when this was done, but we can use humans to get a good output. And if you wanted to, you could do things like figure out, of the people that are in the pool, who are better than others. So maybe if Bob is really bad, maybe we don't hire him next time. Or if Sally is really good, maybe we pay her more and we could give her slightly longer sentences. So there's all these different tricks you can play. First of all, to make sure your workers are happy, because if they hate the job, you're not paying enough, you're not going to get them. Or thinking about, now as I better understand a different worker's strengths and weaknesses, then I can better use them. Okay, no questions yet. Then I'm going to move on to one more thing before asking explicitly for more questions. So,
can I actually ask a question?
Yeah, please.
So I didn't quite get how you decide which work you're doing right. I know you explained it, but I didn't quite wrap my head around it.
Yeah, so that's one of the big problems. So if, let's say I want to label cats, and I have someone come in and just go through and start giving me data that all of these dogs are actually cats. So if I don't actually know the right answer, then I'm just in trouble. One of the things you can do is have gold standard questions. So for instance, show some questions where you know the answer is cat or not cat. And then if a person is not giving you labels that you know are correct, then you can throw them out of their pool and you can throw their data out. If you have a new question and or say a new image and you really don't know what's there, you could ask 3 people, is this a cat or not? And if they all agree, great. If they don't agree, maybe you ask 2 more. Or maybe this is a really important cat, and maybe you ask 11 people, and only if 9 of them agree, then you go on. So you can get multiple presentations. So in our example, we can have some kind of overlap. And if we have an overlap, that gives us better chance of finding the right text. And the more overlap we have, or the more redundancy we have, the easier it is to find out if there's a bad actor, if one of the Turkers is not doing what we asked them to, and the higher quality results will get out. Did that answer your question?
Yes, definitely. So I think that's where measures of annotator agreement, I don't remember the exact metric name, but is that where those kind of things come in?
Yes, exactly. Yeah, so thinking about inter-annotator agreement, or you can look at speed of typing, and there are all these different things that you could use to figure out who you want to trust more or who you want to pay more in order to keep them around longer.
I see. So essentially, what you're suggesting here is you either judge quality based on some sort of a gold standard that you have, and if you don't have that, you rely on a statistical agreement to judge what is good and what is not.
Yeah.
Okay, perfect. Thank you.
Yeah, and there's a question in the chat saying, could you play them a flat rate or look for bad answers, and how to best pay Turkers is an ongoing area of research. Because, for instance, there's results suggesting that if you pay Turkers more, they will work longer, but they won't necessarily work better. Another scheme is thinking of kind of a hierarchy where you have a bunch of people that are doing stuff, and then you have someone else who's a little better paid going and making sure no one screws up. And then as these workers get better, you can promote them. So it's kind of the more office-like environment where you get increasing responsibility, but then as you get more responsibility, if you mess up, then it's going to have bigger and bigger effects. But figuring out exactly how to incentivize Turkers is a really interesting problem. And there are some rules of thumb if you're interested in that kind of stuff. How does RL fit in here? Yes, so I've used Turkers in an RL system. So we've got our agent interacting with an environment. That's not an E, that's more of an E. And then I had Turkers go and look at all of this and try to figure out where was there a mistake. And you can use that to help the agent learn. Or you could have Turkers say, oh, the agent went up, but it really should have gone left. And if 3 out of 5 agree with that, we could give that advice to the agent. But thinking about this human interaction, human AI interaction could fit on top of an RL agent. In this case, we're not even using a machine learning algorithm so much. Here, we're just using an AI system, but it could also be used with supervised learning and unsupervised learning. Figure out who's better. Absolutely. So if as you get more data from your Turkers, you can absolutely figure out who is faster or more accurate or better, for whatever better means. And one common idea is that we have some task and we get a bunch of Turkers to do it, and then we take the top 20% and bring them to the task we really care about and tell them, you did so well on task 1. Now I'm going to ask you to go on to task 2. And by the way, I'm paying you twice as much. And that can totally be worth it just to get the slightly higher quality data. Okay, awesome. Thank you for the questions. Keep them coming. So the next system, so this was kind of an AI system interacting with Turk. Here's actually an ML system. And it could be interacting with Turk. In this case, it was non-Turked humans. But the idea behind calendar help from MSR was you could have different levels of assistant. So you could have fully automated for the easy stuff. if the automated system gets confused, let's ask some people who don't have a lot of training. Maybe these are people from Turk. And then if they get confused, then we can ask an expert. And the expert's time is much more valuable. Now, the cool thing, so one point is the top arrows. As things get confused or we get in trouble, ask for more and more specialized people. The cool thing, though, is we're collecting data from these people. Let's use them to improve the system. So calendar help, I believe it was integrated into Exchange, where someone would say, hey, Matt, could we meet at 9:30? And calendar help was supposed to go and figure out, am I free at 9:30? Do I have enough information to schedule that? Do I know where it's going to be? If I'm not free, can I send some counter proposals? And with this basic setup, they can say, well, we first get the request type. And if it's not a meeting request, immediately kick it off to a human. Sorry, calendar help can only do meeting requests. Schedule, reschedule, cancel, update. Oh, yeah, well, can also handle spam, kind of. But then, okay, so let's say it is some kind of calendar related thing. Then let's see if I can extract the information I need. If so, let's try to get a time that everyone agrees on, and schedule it. And if at any point something's not happening, then it gets kicked up to a human. Now, one of the neat things they found is a lot of the times they would send out, well, okay, for the three of us, it looks like we could meet at 9, 10, or 11. Which do you want? And one of the big things they found is that a lot of time people just wouldn't respond. And it's not clear whether they wouldn't respond because they were lazy, if they wouldn't respond because this wasn't the way they were used to doing it, or if they wouldn't respond because it was an AI. And it was only when the request was coming from a real person that people actually responded. But I really like this system because it's able to leverage humans and learn from them. So it's accomplishing the task and improving the automation. So another example of a human AI system is from AI Redefined. And there they were working with a company or actually a city in Asia to look at vehicle dispatching. So you've got a certain number of dispatchers who handle the emergency calls, and then they need to schedule where the ambulance is going, where the police are going, where the fire truck is going. And there's only so much they can handle. So at some point, they may become overwhelmed, and there could be some easy calls that an AI audit agent could handle. Or maybe things are really chaotic and the AI agent can't fully handle things, but maybe you could realize the person is busy and suggest some things so that the person can quickly look away from the ambulances that they're scheduling and look back. Yes, I agree, we should deploy one police car. Now, one of the reasons this is a great example is if you're a dispatcher and someone calls up trying to order a pizza, it's not because they're trying to order a pizza and they misdialed. It means they need help and they're in a situation where other people can hear them and they can't say that they need help. So if a computer hears can you order me a pizza, it's probably going to miss that subtlety. Now, of course, we could absolutely hand code that one rule so that doesn't happen. But there's always that chance that there's going to be something that a human would catch that a machine would miss, at least for now. And because this is life or death, you probably really want a human in the loop. Yeah, there's many things I'd be nervous about trusting AI with. But I think this is a great example where I think it's easy to see why you really probably do want a human in the loop here. But if too many things are going wrong at once, getting automated support to whatever degree is appropriate could absolutely work or be useful. So these were all virtual interactions. You could also have physical interactions. So this is from my friend Brad Hayes, and here, he's doing a wire routing task. So he's trying to connect some wires so an LED turns on. So he's going to put on one wire, and then the robot's going to help him out. So the robot figures out what he's doing, goes and gets a wire, which will make his life easier, and then brings it closer to him. And the robot doesn't even hit him once. Look at that. So this means the robot needs to understand what the human wants to do, needs to understand what the human is doing, and how it can help the human. So this, okay, I thought that was kind of obvious. But what I really liked is the next thing. So here, the robot's going to help with suboptimal plan mitigation. So what happens? There is a suboptimal wire 4 right next to the board. Well, we'll find out that it's suboptimal. So Brad's going to do this thing. He's going to update the state of the world. And then the robot realizes, ooh, he might do the wrong thing. He might go for the suboptimal wire. So I'm just going to yoink. So if you're building IKEA furniture and the robot's worried that you're going to use the hammer instead of the screwdriver, the robot could hand you the screwdriver, or it might be easier for it to steal the hammer. So I thought this was kind of a subtle way of telling the human, don't be stupid. But okay, so this is for a pretty well-defined task. You could also, it doesn't trust the human. You could also think of when you have teams doing very important and dangerous things. So if two police are going into a building, they're probably going very slowly and they're backing each other up. If the one in back can't really see what's in front of the one in front. If the one in front starts going slowly, then you keep going slowly. If the one in the front turns around and runs, you probably want to turn around and run too. So that's a teamwork thing. However, if there's a person in front and there's a robot in back, if the person in front turns around and runs, that's probably the time where the robot does not run. Because if it can get in between the threat and the running human, that's a win. So there's going to be very different types of teams depending on whether they're humans and robots and what their composition is. And here, really understanding what your teammate is doing and why, and how you should react because of that action. That's going to be pretty important. So if you have a human-robot team that trains together for a few months and then goes into a situation, that's very different than a random cop and a random robot get thrown together at the scene and have to suddenly do something. So these are different settings where if you can build up that trust and understanding over time, then the team overall can perform much better. Now, this idea of teaming and trust and understanding leads into one of my final examples. So thinking about, let's say I'm an oncologist and I'm trying to diagnose cancer. I could have a system that helps me. So this system on its own, it doesn't do a great job, but the system could help me better diagnose cancer. Now, what happens if the system performance gets better? Well, that's a win, right? Anytime the system gets better, then the team should get better. And this paper by Microsoft Research argued that's not always true. So for instance, if going back to thinking about the doctor knows this system is really good, except on women over 70. So I'm going to listen to the system a lot, but when it's a woman over 70, I'm probably not even going to ask it. Now the system gets better. And now it's really good at women over 70, but it happens to get a little bit worse at everyone under 40 years old. So the total amount, if you're just trying to minimize the mean squared error, the greater good, the AI is doing better. But now the doctor might be listening to the robot in the wrong places, might be listening to the agent in places where it shouldn't listen. So the way they tested this, I thought was pretty cool. They said, all right, you've got some widgets, and for each of these widgets, you need to say, is it defective or not? So I can either say, well, yes, it's defective. No, it's not defective. Or I don't know. I need this other system to tell me. So if the system says, if the AI says it's defective, and I say I accept your decision and I'm right, I get 4 cents. If the AI says this is defective and I say you're wrong, I lose 16 cents. Or at any point, I could say, I don't know, let's ask the expensive system. So here, the human can learn based on these features when the AI is right or wrong. So for instance, it may learn that the AI is always right unless it is a blue circle. If it's a blue circle, I don't want to listen to it. However, if it was a blue triangle or if it was a red circle, then it's fair game. So the human can learn when to trust the agent. And what they showed is, okay, the human can learn when to trust the agent, and then we could do a few different things. The first one would be to do nothing. There's no update to the agent. We just do exactly the same thing. And then we just get this straight line. Or we could make the agent better, but in an incompatible way. So for instance, if it was always wrong for blue circles, now maybe the robot becomes better, but you really can't trust it for anything blue. Then in that case, the team performance goes down. Whereas if you do updating in a certain way, if you have AIs improving or machine learning agents improving their behavior in a way that's consistent with the human's expectations, then you can increase performance. So if you're thinking about a human AI system, if the human all of a sudden got some new training, the AI should probably account for that. Similarly, if the AI starts changing how it makes decisions, the human better know about that, or at least the AI should be updated in a way that won't hurt. Yeah, and so there's a great question. Why not just tell the doctor where the AI is wrong? So if we knew that the AI was wrong on women over 80, we should absolutely tell that to the doctor. Or if the AI had some estimate of confidence and you could see that the AI was less confident in women over 80, that's another great solution. In this case, they're assuming that the AI isn't that introspective and doesn't have that ability, because sometimes it doesn't know what it doesn't know. Okay. And another thing you could think of doing is talking about, well, what happens when the AI in my team just isn't doing what I want it to do? And this is really where we start getting into the machine learning, reinforcement learning setting, thinking about, well, I've got this agent that's working with me and we should work together. So I should be able to teach it when to clean the litter boxes, not when I'm sleeping. I should be able to teach it when I want it to do different behaviors for me. I should be able to, teach it how to play ping pong with me, or I could even think of teaching it like a dog. So I could do demonstrations, or I could say good robot, bad robot. Now, one of the things I really like to see is you come into the kitchen and you start trying to teach your robot how to carefully julienne a vegetable. And then I just would love to see you coming down in the morning and the robot's been up all night and it's just there waiting for you, sharpening its knives, ready to show you that it can julienne the heck out of that cucumber. Not creepy at all. But we want, and this is not just AIs doing things for us, but doing things with us. So thinking about that human AI teaming and how the agent can learn to be a better teammate. So where does this leave us? If this is interesting, well, okay, so what are the next steps? So if this is interesting, I did run an entire semester-long course last fall where we talked about interactive humans and machine learners, humans and supervised learners, humans and reinforcement learners. We talked about some of the ethics behind it. We talked about how to identify good problems where a human and AI could do better than either alone. So there's a bunch of content here, and these slides will be up on ai.science. But it's all free. There's a bunch of guest lectures, all of that. There's also pointers to other resources if you're interested in this kind of stuff. But in addition to more questions, sorry, one more slide. If we're thinking about where we want to use human AI, again, think about what's the return on investment? How useful is this going to be for me? Because it might just be easier to hire another person. What's the risk? That's not just how risky is it that this will fail, but it could be how risky is this situation if it is partially automated? And will there need to be trust? If the robot is handing me things, it's not that big a deal. If the robot is handing me knives, maybe a little more trust is needed before a human's going to agree to do that. And thinking about the big thing that I've been thinking a lot about is what is easy or difficult. So, for instance, in a military situation, you could think that a human might be very good at strategic reasoning. Or think about StarCraft, figuring out when you want to rush the enemy versus build your tech tree. Whereas an agent is very good at tactics. So the agent can control 30 Zerglings very precisely. The agent can control 4 UAVs or drones at superhuman speeds. If you can get the benefits of both of these, you'll be able to outperform, I argue, be able to outperform just a human or just an AI. In building up this team expertise, what is this team good at? How can we get the team to be better than its individual components? So I think intelligence augmentation is something that we have not been talking about enough, that there are many situations where we don't want to be fully meat controlled, and we don't want to be fully silicon controlled. I do think there's some low hanging fruit there. And so we have time for questions, but I'd also really like to spend some time brainstorming with you about if you have any problems in your domains, or if you have any thoughts off the top of your head where a human AI or human ML collaboration could be superior to just humans or be superior to just an AI solution. So thank you for listening.
Thank you so much, Matt. Hopefully you have a bunch of questions. But this was very interesting for me also because, as we are building our content curation platform, a big part that we realized very quickly was that, machine alone is going to be probably very, very bad at curating knowledge. And a lot of what we've been doing was along these lines. So this has given me a bunch of interesting ideas to think about. So definitely directly related to our platform. Awesome. Any questions, anybody?
Hey, Matt. Great talk. Thank you. My first question, I don't have any problem that I would like to discuss with you, but I have a concern. So what are the best mechanisms that you can think of to provide feedback to your automated systems? Now that the human in the loop has realized some defects, how do you kind of improve or get that kind of virtual cycle where your automated systems can get that feedback and improve its predictions, let's say?
Yeah. So for if we were doing predictions, you could simply have the human say, your input was X and you said Y, but you should have said Y1. So it could be just a simple correction. You could also think about, though, if there is some way to say it should be Y1 because. And this is really where the interpretability comes in. So if the system thinks it's perfect and it is making predictions that you know are incorrect. If you can figure out why, then hopefully you could poke the system so that it improved in the right direction. Another thing you could do is say, well, I can see that ball is blue, and you said it was orange, so I'm going to give you a blue cube, and then I'm going to give you a blue triangle, and then I'm going to give you a blue house. So you can change the data set to force the agent to really get higher accuracy in the areas you care about. And if that's not successful, then you've probably identified a bug.
Really interesting, Matt. As a matter of fact, I'm part of a team that is participating in a AI science competition, and we're identifying some predictions where clearly, the AI is doing wrong, and we are reinforcing with some concept, with some basic principles. We are providing those principles to just reinforce those concepts into the system. So very valuable. Thank you.
Cool. You're welcome. Oh, one other thing I'll mention is, let's say the system wants you to dispatch 2 police officers to this place, and the human says, no, we don't need any police officers. If the AI had theory of mind, then the AI next time might say, you should dispatch 4 officers to this location. And the human's like, oh man, well, I don't know, I'll just dispatch 2. So what happens if the AI starts anticipating the human's actions and giving false answers so that the human AI system achieves the goal that the AI wants? That's more science fiction than science right now, but that goes back to thinking about alignment between the AI and the human, and they really need to have that shared goal. If there is misalignment, the team can suffer.
Hi, Matthew. This is Madhur. I had a quick question for you in terms of something that you spoke about during the first session on 22nd. So, you said something about explainability in reinforcement learning models, and it's not as easily achieved. So, what are some of the suggested ways from your end if somebody wants to know that at the end of the whole process where you got some inputs from supervised learning to decide that these are the fair inputs that I'll put into my reinforcement learning model, and this is my final outcome, it is coming how I expect it to be. Then what are some of the suggested ways in which we can come to some of the basic variables that were key in determining those right results through reinforcement learning? I mean, on the explainability side of it.
So, okay, a few answers. The first one is, let me make sure this is the right one. Yes. So, Christopher, whoops, stop, go back, cancel. Awesome. Let's try this again. Here, let me just do this. I'll just enter a new slide. So then I can take notes and you can see it. So there's this guy. Okay, I'm just going to say it and I'll put it into the recipe later. Actually, hey, I can share my screen. So there's Christopher Molnar, who has a book on interpretable machine learning, and it's all online for free. So this has a bunch of the go-to methods. This is one place you could start. Another thing you might want to consider is Cynthia Rudin, and this whole explainability has been her work, and she just came out with a great archive paper on open problems in explainability. So for reinforcement learning, there's not a whole lot of good solutions right now. If you're looking at supervised learning, there are absolutely ways you can do this. The 2 big distinctions is it interpretable or explainable? So usually people say something is explainable if you take a black box, you take a neural network, and then you put something on top of it. So for instance, you could have a picture of a cat, neural network says it's a cat, and then you go and start poking at the pixels. And it could turn out that if you changed a few of the pixels on the cat's nose, you get the result of dog. That would suggest that the cat's nose is very important, and changing the pixels around the nose is more important than changing pixels around the ears. That's a way of bolting on explainability on top of a black box model. Cynthia's argument is that we should be using interpretable models. We should be using things like shallow decision trees. And she has one famous example where she took a commercial system, which is closed source, and was able to replicate that classifier in, I believe, 4 human readable rules. So she argues if you can get the same performance with human understandable machine learning approaches, then you shouldn't be going directly to deep neural networks. Why not at least try things that humans can directly understand? But I really love the question, because I think that's one of the things we as a community need to do better, machine learning researchers, but also it's going to be really helpful as we solve this, as we get a better handle on explainability and interpretability. It'll be easier to form these teams. It'll be easier to deploy these models, because it will be easier to trust and understand.
Thank you, Matthew.
Okay, and then there's a question, a comment in the chat about high stakes collaboration. Maybe the AI could do the dirty, dangerous, or dull part. Let's see, which can help the human make decision where the AI can't. Right. So figuring out if in the RL setting, if the agent is able to raise its hand and say, "Help, I'm confused," that's perfect. And you can also have the human watching the agent, so at any time you could hit the big stop button and say, "Oh boy, you're about to mess up. Let me save you." So it can absolutely be bidirectional. And the theory of mind is exactly something that we have to think about in these multi-agent systems. So for instance, if the AI agent just assumes the human will do whatever it's going to do, and then it's going to do what it does, it's not all that interesting. If the agent can reason about what the human is going to do, maybe it can anticipate the human and help provide them things before they even know it. Conversely, if the human understands the agent, if, "Oh man, I'm worried the agent's going to try to go through that door, and I really don't think that's a good example. Maybe I can do something proactively to convince the agent not to go through that door." And that could be a communication, or it could be implicit communication by you changing where you're standing. The problem with theory of mind is it's possible to get into that recursive loop, right? I think that he thinks about me, that he thinks that I think, that he thinks that I think. So at some point you have to cut it off. But figuring out exactly how agents and humans should model each other, how they should think about each other, is really exciting. And I don't think people have really looked at that in the context of explainability.
Wait, can I add something, Matt, super
Please.
quick? So I think, you described like the first order theory of mind. Is there like a benefit to going just to like second order where, like I'm thinking about the game, there's a card game called Hanabi where you kind of like—
Hanabi, yeah.
Yeah, you can kind of like see what your neighbor has, and if there's like a game player there, would they need to consider this like higher order theory of mind?
Absolutely. So that you can think about level K reasoning in general. So if your opponent is a level 2 reasoner and you are a level 3 reasoner, then you can probably beat them. If you're in Hanabi and your friend is a level 2 reasoner and you're a level 7 reasoner, then you probably need to adjust downwards, or you're going to be making assumptions because you're thinking that, well, because I played this card, he's going to know that I have a red, and he's just not following along. So there are so for instance, I recently saw a work where the agent assumes its opponent is either a level 0 or a level 1 and figures out how to best play against them based on what it thinks its reasoning capabilities are.
I see. Thanks. And just another question about the learning to abstain. Like, so in robust supervised learning, there's like a formal literature on supervised learning systems they're really learning to reject, to make a choice, or they kind of like or learning to abstain? Is there like a formal theory in RL for like abstaining, or is that just part of the action space, like to abstain?
So it depends what you mean by abstaining. So there in RL, there's always there can be the idea of take no action or don't take an action, wait and collect more data. That's one kind of thing. Another is the idea of I don't know what's happening. I just need to ask for help. But a third way I might interpret your question is thinking about a reward alignment. So if I'm a robot and I'm trying to do this thing, and the human is teaching me by hitting a big red button when I do the wrong thing, the robot might be incentivized to cut the wire between the big red button and itself. So by doing this, it has completely made sure it can't get any bad rewards, and that's absolutely not what the human wanted it to do.
Got it. Yeah, by learning to abstain, I just meant it's from Cortes, like the early SVM literature, where let's say you have a multi-class classification with 5 classes, you can learn robustly, and the learner that you've trained, it has another option to choose not to predict if they think that they're not going to do well. So so it's not part of the label space in the training data. It's just like an extra option that that learner can make. And then there's whole theory about like it having the best empirical risk, etc.
I think a related framework is Quick. KWIK knows what it knows. There, it gets a sequence of inputs, and it needs to classify them. And it can say, "I don't know." You can say, "I don't know, I don't know, I don't know," and then as soon as it starts giving labels, it has to be 100% correct.
I see.
And you want to bound the number of times you have to say, "I don't know."
Got it. Thanks.
Yeah.
So, Matt, what is the relationship between what you talked about today and, just gonna throw out buzzwords, active learning and swarm intelligence?
Whoa, those are definitely buzzwords. So I think it's very related to active learning, because you could think, well, I've got an agent and it just wants to learn stuff, so it can ask for help. And in active learning, you often assume you have an oracle that you can query for some cost. The main difference here is if we have a human or another agent, typically in these team situations, we don't assume they're perfect. So you normally take that into account. And there could be times where they know a whole lot about one thing, but are completely rubbish at another thing. So trying to understand where your teammates may be better or worse can absolutely be useful. And you probably do want to minimize the number of times you poke the human and say, "Hey, what's this label?" And then swarm intelligence. So typically when you talk about teaming, whether it's agents or human agent systems, you're thinking of a group of physical or virtual things that can kind of reason about each other. And like, I know Bob's really good at going through doorways and Charlie's good at flying. When you talk about swarms, or this also comes up in mean field reinforcement learning, now instead of thinking about my teammates, I'm thinking about a distribution. And it could be just a large distribution of my friends. It could be a large distribution of attackers. But I'm thinking at this higher level. I'm not thinking about exactly what Bob is going to do, but what are those 100 agents going to do together? And I don't care which one of them actually gets to the finish line. I want to reason about what's the chance that one of them will get to the finish line. So when I've seen people talking about swarms, it's usually more of that collective. And there, I think one of the really relevant things in AI, human AI interaction, could be human swarm interaction, and thinking about how the human can give high level directions, such as this is the general place you want to go, or this is the reward function you want to maximize, or this is the task you want to accomplish it. And then the swarm needs to self-organize in order to accomplish that task however it's able to.
I see. So if I want to reiterate what you said, essentially in swarm intelligence or in swarm situations, the agents are homogeneous and the task they're trying to carry out is something that they want to do collectively. It doesn't matter how they do it. But when you're talking about teamwork, you're talking about potentially heterogeneous agents that are trying to carry out a task, and each of them might take a responsibility in carrying out that task.
I would almost agree with that.
Okay.
So if you think about a human agent team, those would definitely be heterogeneous because humans and AIs act very differently. Different AIs can act differently. In a swarm, you're right. Most of the time, they're homogeneous. But you still could think about, I have a swarm of UAVs that are fast and UAVs that are slow but can carry more. And as long as I'm thinking about this half and that half, rather than agents 1, 2, 3 versus agents 4, 5, 6, then I think you can still think about the difference between team and swarm. But this is all, these terms will mean different things to different people. So these are exactly, anytime you're interacting with someone who starts throwing, well, usually any kind of terms around, it's really good to make sure you write down what you're talking about, because so many times I've had a discussion with people, and then like a week later, we realize we are completely talking past each other.
Awesome. Thank you so much, Matt. As usual, very, very engaging. Appreciate it. Please. Thank you.
Thanks for all the questions. That was fun.
Thank you, Matt.